Neural networks do not always learn smoothly. A capability can appear suddenly, while the ordinary loss curve barely hints that anything changed. This paper asks whether hidden developmental stages are written into the geometry of the loss landscape. The authors track a singular learning theory quantity called the local learning coefficient throughout training. Its plateaus divide two transformers into stages, and most boundaries coincide with interpretable changes in behavior or internal structure. The evidence is suggestive, not causal. The study shows that changes in degeneracy coincide with development in two small transformer settings. It does not prove degeneracy causes the circuits, or claim these exact stages are universal in larger models. The paper trains two deliberately small models. One is a two-layer attention-only language transformer on the pile with about 36 million parameters. The other is a two-layer transformer with about 700 parameters trained to do linear regression in context. The overview already reveals the central surprise. Test loss descends fairly smoothly, but the LLC rises, falls, and pauses. Those pauses define 5 stages in each model, with distinct stories: linguistic pattern learning on the left and task inference on the right. Degeneracy means some parameter changes barely affect the represented function or loss. Neural networks have many such redundant and higher-order directions. Ordinary curvature sees only the local quadratic approximation, so it can miss the geometry that matters in singular models. The local learning coefficient is defined by how quickly the volume of near-optimal parameters shrinks as the allowed excess loss approaches zero. Lambda is the exponent in that volume law. A smaller lambda means a more degenerate neighborhood. A quadratic direction contributes 1/2 to the LLC. A quartic direction contributes 1/4, and an unused direction contributes nothing. That is why two landscapes with equally zero Hessians can still have different LLCs. The higher-order degeneracy is different. The authors visualize 4 two-dimensional landscapes with decreasing LLC. The wells are not just getting wider. They're qualitative algebraic structure changes, which is precisely what Hessian eigenvalues cannot fully distinguish. Exact LLC computation is generally intractable, so the paper estimates it around each training checkpoint. The estimator measures how much higher the sampled local loss is than the checkpoint loss, scaled by effective dataset size and inverse temperature. Samples come from a localized Gibbs posterior. One term prefers low empirical loss, the other tethers weights near the checkpoint. Beta controls temperature and gamma controls localization, so tuning them determines whether chains explore usefully or escape. Stochastic gradient Langevin dynamics approximates that local posterior. Every step combines a loss gradient, a restoring force toward the checkpoint, and Gaussian noise. Multiple chains estimate the expected loss increase around the same weights. The measurement is expensive. For the two-layer language model, the main configuration uses 20 chains with 200 steps each, and estimating all checkpoints took roughly 200 100 GPU hours. For regression, 10 5,000 step chains can take up to 72 CPU hours per run. The appendix is unusually candid about estimator failure. 2 large steps cause numerical explosions. 2 small steps fail to mix, and weak localization lets chains escape to a better optimum. Online LLC traces are used to detect these pathologies before trusting a stage boundary. The motivation comes from Bayesian local free energy. One term rewards lower loss linearly with sample size. Another penalizes complexity through the LLC times log sample size. As data grows, their balance can switch which solution neighborhood is preferred. Figure 3 illustrates a sudden posterior transition. One solution is more degenerate but has worse loss. Another is more accurate but more complex. At a critical sample size, their free energy curves cross and the preferred neighborhood changes. Operationally, they smooth LLC over log training time with a Gaussian process, differentiate, and identify plateaus where the absolute slope is near zero and locally minimal. Once smoothing and tolerance are fixed, boundaries are selected automatically rather than by inspecting behavior. The language model is trained for 50,000 steps on roughly 5 billion pile tokens, with context length 1,024 and a truncated 5,000 token vocabulary. It has 2 attention-only layers, 8 heads per layer, and checkpoints every 10 steps. The 5 language stages tell a coherent developmental story. First, the model learns bigram statistics. Then it uses position to memorize common longer phrases. Next, previous token heads form, followed by induction heads and measurable in-context learning. No clear interpretation is found for stage 5. From step 0 to 900, the bigram score approaches within 0. 3 nats of the irreducible bigram entropy. The model first learns the best next token rule available from only the current token, before exploiting longer context. Between 900 and 500 steps, positional embeddings become useful and scores improve sharply on common trigrams and foregrams. Appendix visualizations show better predictions for tokenized words like Linux, Python, database, and framework. From 500 to 17,000 steps, the induction circuit assembles in 2 phases. First layer heads learn to copy previous token information. Then second layer prefix matching heads complete the circuit, and the in-context learning score improves. The appendix compares logits across stage boundaries. Red highlights expose improved bigrams, then longer common words, then repeated names such as Dursley after their first occurrence. The LLC did not supply these interpretations. It told researchers where to look. The second model receives a sequence of input-output pairs generated by one hidden linear task vector. It must predict each next y from the preceding examples. Because the optimal solution is understood, this setting cleanly separates task prior prediction from genuine in-context inference. The regression transformer has 2 layers, 4 heads per layer, and 51,717 parameters. It trains for 500,000 fresh batches, or 128 million sequences, with 4-dimensional tasks, up to 8 in-context examples, and 5 seeds for replication. Again, the LLC divides training into 5 stages. The model first predicts the task distribution mean, which is 0 here. It then acquires robust in-context learning. Later, typical performance keeps improving, while extreme input robustness worsens and layer normalization weights collapse. During the first 1,000 steps, output magnitude falls toward 0, below even the target noise variance. The model is learning the optimal context-independent prediction. Use the mean task vector before attempting to infer the task from examples. In-context learning is measured as later token loss minus earlier token loss. More negative means the model benefits more from context. During LR2, this score drops, although the appendix shows early token task localization improves before later token refinement stabilizes. The model then specializes. It continues improving on ordinary inputs and unusual task vectors, but performance on large magnitude input vectors first improves and then degrades. Training has built a stronger in-distribution algorithm at the cost of a particular kind of robustness. At the same time, embedding dimensions, attention patterns, unembedding weights, and layer normalization weights partially collapse. Many dimensions become tiny or irrelevant, making the implemented computation effectively simpler and offering a plausible explanation for the LLC decrease. Layer norm collapse occurs even though the regression model uses neither weight decay nor dropout. The authors call this a clear example of implicit regularization. The optimizer or architecture favors a simpler, effective solution without an explicit penalty. Across 5 seeds, both settings recover broadly consistent early stages. Regression has remarkably little seed variance, while late language model stages vary more and sometimes subdivide. This supports the method, but also shows that stage boundaries are not immutable constants. Hessian trace and maximum eigenvalue detect only one of 4 regression boundaries found by the LLC. They emphasize maximum curvature and miss higher-order degeneracy. The authors also report LLC estimation scaling roughly linearly in parameter count versus quadratic storage for a full Hessian. The strongest limitation is causal. Structural collapse and LLC decreases happen together, but the theoretical arguments assume exact 0 weights and infinite data limits. The estimator is also used away from true local minima. Stage detection depends on smoothing and tolerance, and the studied models are small. This paper's real contribution is a search strategy for interpretability. Measure a setting-agnostic geometric signal throughout training, use it to locate hidden transitions, then investigate what behavior and circuitry changed. The loss tells you how well the model is doing. Degeneracy may tell you when it became a different kind of model.